Welcome back to Dardres Education. Imagine you need to start a massive three-phase induction motor. It's connected to a heavy load like a giant industrial fan. You decide to just flip the switch and connect it directly to the power line. This is called direct online starting, or DOL. When you do this, something violent happens. The motor is at a standstill, so it acts almost like a short circuit. It pulls a massive inrush of current from the grid, sometimes 5 to 7 times its normal full-load current. The lights in the factory dim. The mechanical shock on the motor shaft is brutal. The windings overheat. For small motors, this is fine. But for large motors, this huge electrical spike is unacceptable. We need a way to gently wake the motor up. We need to start it with a lower voltage, and once it's spinning, give it full power. Enter the star delta starter. An elegant, purely mechanical trick of wiring that solves this problem perfectly. To understand how it works, let's open the terminal box of a standard three-phase motor. Inside, you don't just see a black box. You see the ends of 3 separate electromagnetic coils. These are the stator windings. Let's color code them. We have the U-phase winding in red. Its ends are labeled U1 and U2. The V-phase winding in amber, labeled V1 and V2. And the W-phase winding in blue, labeled W1 and W2. To make the motor spin, we must connect our three-phase power supply, L1, L2, and L3, to these windings. But how we connect these 6 terminals together changes everything. Let's look at the first configuration, the star or Y connection. We take the bottom ends of all 3 coils, U2, V2, and W2, and wire them directly together. This creates a common neutral point. Then we connect our power lines L1, L2, and L3 to the top ends, U1, V1, and W1. Visually, the circuit looks like a Y or a star. Now, here is the magic physics. Let's say our line voltage, the voltage between any 2 phases, is 400 volts. Because of the star geometry, the voltage across any single winding is not 400 volts. It is divided by the square root of 3. 400 divided by 1. 732 is about 230 volts. The windings are receiving significantly less voltage. According to Ohm's law, less voltage means less current. In fact, the starting current drawn from the grid is reduced to exactly 1/3 of what it would be in a direct connection. The motor starts smoothly. No lights dimming. No violent mechanical shock. But there is a catch. The starting torque is also reduced to 1/3. The motor is weak. It can get up to speed, but it cannot drive its heavy load efficiently forever in this state. Once the motor reaches about 80% of its full speed, the inrush danger has passed. Now the motor needs its full strength. We must reconfigure the windings into the delta connection. This time, we don't connect the ends together at a neutral point. Instead, we connect the windings end-to-end in a triangle. U1 connects to W2, V1 connects to U2, and W1 connects to V2. Then we attach our power lines to the 3 corners of the triangle. Look at the voltage now. The U winding is connected directly across lines L1 and L2. It receives the full 400 volts. Every winding receives the full line voltage. With full voltage, the motor draws its normal running current, and most importantly, it develops its full 100% torque. It is now ready for heavy industrial work, but nobody stands at the motor manually unscrewing wires while it spins. How does the transition actually happen? We use a star delta starter panel. It contains 3 heavy-duty electromagnetic switches called contactors and a timer. Watch the mechanical ballet. To start, the main contactor closes, bringing in power. Instantly, the star contactor closes, bridging U2, V2, and W2. The motor is in star mode. It hums to life, gently accelerating. The timer is ticking down. 5, 4, 3, 2, 1, click. The star contactor opens. For a fraction of a second, the motor coasts freely. Clack. The delta contactor slams shut, linking the windings end-to-end. The transition is complete. Star for starting, delta for running. It is one of the most clever, reliable, and cost-effective methods in electrical engineering to manage high-power machines. No expensive electronics required. Just simple, beautiful circuit geometry. We are building the ultimate library for engineering students. If you found this visual breakdown helpful, hit like and subscribe to Dardres Education. Happy engineering!